Uh, my name is Chikam. I'm an undergraduate in Georgia's reading course going to my third year. I was under the impression that I was going to be presenting to undergraduates instead of all these well experts in the field. So my presentation was actually aimed towards undergraduate when George said there was going to be a final presentation for my course. So the topics that I go over are probably slightly elementary, but here it goes. So my topic is just going to be something I found interesting about abstract harmonic analysis, which is the Haar measure. And I'll start, it's just basically an elementary overview of the Haar measure. So, okay. So, okay, as I said, this was intentional and originally intended for undergraduates. So before discussing the Haar measure, I would like to explain the motivations of having what is this abstract measure first. Is that let's just talk about a measure in Euclidean space. And a measure in Euclidean space, and I mean by that is that a subset of some subset of Rn, and we're trying to assign a value to that subset, and that assignment is what we call a function. So let's just start with what is a measure first, or the historical parts of a measure. It's and this measure, well, we originally made it satisfy three rules, and then well, this function, let's just call this u for now, mu for now, on E, where E is some subset of Rn, proper subset. Actually, I think we can allow this. It's that this value is some element between 0 to infinity. And then the three rules assigned for it are one, if we have a sequence of subsets in Rn, disjoint sequence, where finite or infinite, we have that mu, well, the function on the union of these sets is equal to mu of E1 plus blah, 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 blah. That's the first rule. The second rule is that it's translation invariant. That means when you, for example, if we have a ball in Rn, well, just a standard unit sphere, and if we move it, and we move this somewhere else in our plane, our function mu still yields the same value, no matter where we move it on this subset of Rn. And the last rule was that mu of the unit cube, just to note this unit cube as C, is always equals to 1, where this unit cube is respective to our dimension. Now, these three rules, as it turns out, while they seemingly look nice, they're actually inconsistent. And I think Fallen, the book, well, Fallen provides a nice proof. I'm not sure the suppose we have a sequence of disjoint subsets in Rn, whether finite or infinite. This should be true. Oh yes, the union. I'm sorry. I'm very sorry. I'm sorry. This? Okay.
Well, I would say that's not standard. Okay. If there are any, you can find someone that uses it. Okay. And then it's that people
anyways, these are actually inconsistent. All these three conditions are, if we hold them together at the same time, they're inconsistent. Fallen presents a proof where you sort of do this in where you take the unit interval, you shift a little bit, chop it a little off. Turns out you get a contradiction. And so we might be tempted to reduce, well, weaken some of these conditions, and in particular condition 1, by saying, all right, like, well, about we just consider finite disjoint unions. And
what does condition
It says, oh, sorry, I'll just say, mu is,
Just say something.
mu is translation invariant. Our function should be translation invariant, where, for example, you have the unit sphere, you just shift it by like 1 unit.
You want it to make sense for all subjects.
Yeah, we want to make sense for all subjects. And when I say translation invariant, I mean shifts and congruence. Well, if two sets are congruent, then they should yield the same value under mu.
Are there any examples of measures that are defined that arbitrary?
A measure 0 defined.
Well, you're saying that I don't quite get what you're talking about. Nobody in their right mind would talk about a measure of arbitrary subset.
Oh, subsets on Rn.
No, of any set, of any large spaces, yeah. That's not what a measure is when you're talking about arbitrary subset.
Well, a measure is the function.
No,
I think you want to use in measure.
on a certain collection of you
Okay.
certain subset.
My bad. I apologize for that.
Well, you don't have to apologize, but just say what you're talking about, going to be talking about. I don't know what's happening. Your half hour is almost gone.
Okay, well, technically I start from 40, but I'll speed up the process. I'll try.
I don't want to speed it up. I want to slow it down and see what's happening.
Okay.
And this is not.
Okay, as a suggestion, you may want to write things.
Okay.
But I don't want to hear anyone talking about a set function to find an arbitrary subset.
Well, on the collection of subsets.
Measure.
Well, measurable subsets of some collection of subsets or Rn. And we may be tempted to weaken consider one to limit our sequence to become a sequence of finite disjoint union of subsets only. But I think everybody in this room knows about the Banach-Tarski paradox, and that is the thing. So in general, measures, we only define them to be consistent on whatever we want them to consist about, which is which highly depends on the space we're working with. And okay, now since this is about abstract harmonic analysis, and now we're talking about the language of topological groups.
We don't want an instructional lecture. We want to report on what you've been doing. That's what we want. That's what I want.
All right, sure. Okay.
Maybe give us like what's gonna be the big thing here?
Okay. I will. Okay, and I will lead up to a proof. I will give a proof of the existence. No, the uniqueness of a Haar measure for locally compact abelian groups, and then well, technically it's not by me. I read a paper on it. It's a proof on the existence of a Haar measure that uses functional analysis for locally compact abelian groups.
Okay, well, that's nice.
Yeah. Okay. So
maybe you want to maybe you would help to say that at the beginning, and then maybe what now we do what should do now. Maybe you outline the steps. But how many steps are there?
Start now. Okay.
Sorry?
Okay. So I'll just go with the.
Whisper it into our ear. I mean, you don't have to write it down. Tell how you're going to construct the note.
So you want the existence?
Well, you said existence.
Yeah. Okay. So well, I mean existence and uniqueness, but existence uses the functional analysis one. Okay, in the existence proof, one uses the Markov-Kakutani fixed point theorem, I think. And then you have to use two lemmas. Lemma 1, should I write it down? I should write that one down, right? I'll write it down.
Well, you know, it's not called putting a lemma when you're just talking about. You say you try to describe what the technique is.
Yep. Okay, lemma 1, it's a lemma about topological groups, and so let G be a topological group. And then N is a neighborhood and an identity in G.
Tell us what the lemma is.
Okay, so we have a symmetric neighborhood in the identity near the identity of G. And then the lemma is that there exists a subset S such that for each element of G, the general topological group, the set here, this set, and by this we mean when we say multiplication of two groups, I think. Okay, I won't explain that part. This set contains at least one element of S, and the set the set. Okay, sorry. This set contains at least one element of S.
Technical level, no one wants to see it ever. You just give the proof, and then the main step, you give the overall outline of the proof, and at a certain point, you say that we're going some technical limit.
Okay.
It's impossible to talk about something like this,
Okay, the two lemmas are fairly technical.
Exactly, so you don't mention, keep them.
Okay. Okay, the two lemmas are fairly technical, and I'll go over them later.
We don't need to know what you just said. We want to know the.
Whoops. Yes, and sorry, one second. Okay. And for the yep, and for the outline of the existence of the proof is that we want to define a space of continuous functions on yes.
Sorry. Am I just starting
from here?
We're not talking about that. No, we're not going to talk about it.
Well, not I'm if I have time. I will try to explain it, but so existence proof using this function analysis proof, I'll just say it's by Izzo, I think. 1992, I think. It's that we want to consider a space of continuous functions on G with compact support. And the space of all linear functionals on G, and then the weak topology on that is using the weak topology induced by the space of the functions with compact support is enough. And then, okay, and then we need to find.
And the definition we're making.
Yeah.
Continuous semi-functional in a certain sense on the continuous functions say compact support. That's everyone would accept if you can just put something like that.
Yeah.
People would be quite happy that's amazing.
Yeah. But the thing about the Haar measure is that we want left invariance, and that's where the fixed point theorem. No, actually I haven't.
Well,
Well, yes.
You don't have any revealing case in order to clear out
Mm-hmm.
Okay, so
Left and right, yeah.
And you have some nice fixed point theorem.
Mm-hmm.
We'll take the topological vector space of continuous functions with compact support.
Yeah.
And construct a linear functional, which is invariant.
Mm-hmm. Yeah.
How do you get uniqueness?
Uniqueness, it's the fairly standard computational proof. It's the fairly standard computational proof, I think. Where you basically show that first you need to find a specific function that's of one of these functions with compact support, positive functions, and we will show that basically for two Haar measures on the topological group, mu and they differ by constant, basically. That's the general idea for every single uniqueness proof of measures, I suppose. But
so that's the definition of uniqueness.
Yeah.
Nothing computational about that.
Okay, I'll demonstrate the steps for the computational part.
Well, everything is a part of computation.
Well, I suppose.
It'd be nice to.
Okay.
For like it.
Pardon? In the case of a sorry, I have hearing problems. So
In the case of the contract group, you can make it even. You can make it absolutely unique, right? You just say the measure of the whole group is equal to 1. If you say that, then it would have to be absolutely unique, right?
yes, it would.
But is that easier? Is that any easier to prove?
Well, I'm not too sure about that.
It'd be nice to get some idea of why it's unique. For instance, we take the product that we direct some of two in top right.
Mm-hmm.
Contact.
Yeah.
You'd almost think that each one is the measure of each one is unique up is only unique up to a constant.
Mm-hmm.
Then what does that say about the product measure? The measure on the Cartesian product, and an obvious measure on the Cartesian product. Then how would you get to that? To change the two measures on the two components, it can change independently.
Yeah. Well, you're trying to use, are you talking about compact groups here? Oh, then you can just change the two measures around. Yeah.
But the non-uniqueness here is talking about a single parameter. The two vectors are one of the multiple. But if it's product space, then any measure would be a product of two measures.
Yeah.
At least if you could take the product of two measures. And then, but then each one is non-unique up to a point. So that's a priori, that's two parameters.
Yeah.
So how does that result in the single parameter?
Well, basically, it could be when you say that the product of the measures is that you can have
multiply the first measure.
Yeah.
By something, multiply the second measure by something. So why is that not? Why this says uniqueness up to a single. Why would that be true for the setting on the top of it? But there's no a priori of two parameters.
Well, these two parameters are the same, no?
No, it's two completely separate local compact computing groups. And each one, there's a C1, the real one, and the okay, let's call them the two measures are mu and nu.
Okay.
No. You have two measures on the first group.
Okay.
Two measures on the second group. And then
G1.
But the two, one, if you look at the two first measures, one is a multiple of the other.
Yeah.
The two second measures are one, again, one of them is a multiple of the other. So each one is a multiple of the other.
Yes.
So how does that come down to a single value? That's two values. That's two values.
Good.
Sorry, let me ask you a question.
Yeah.
The third condition doesn't force C to be 1.
It doesn't force C to be 1. There is
Because if you and must satisfy 3, C should be 1.
You're talking about the compact case again.
Gary didn't have anything
No,
about
no, but
C is a compact there.
C is the
That was unrelated to groups, the local compact.
Okay.
Unrelated to local compact. That was just general. It was the general theory of finite measures. But our measure is never going to be finite unless the group is compact.
Yeah.
Okay. So we do have a arbitrary balance. If it's if you have two local contractors to look at the product,
Hmm.
then two measures on one and two measures on the other. In each case, you've got a constant coming in. And so how does that convert into a single constant that they combine to?
Well, in the case of, I'm not sure if I'm recalling this correctly, is that in the case of a single group first, these two measures are equal if, I think there's something called homogeneity or, okay, never mind, throw that out of the window. But in the case of two groups, if you're taking their product, then two parameters.
So you have a constant for the first group,
Hmm.
relating the two measures there, and you have the constant for the second group, relating the two
Hmm.
measures there. And if you combine the two first measures and the two second measures,
Hmm.
each group has a first measure and a second measure.
Hmm.
Combine the two first measures, you get one measure on a T cross, T1 cross T.
Yeah.
Then the thing, there's a two second measure. So the two measures, and in order, you have two constants relating with the product mix.
Mm-hmm.
And I'm just wondering how that is consistent. Here's one introduced the word.
Oh yes, that's okay. We're talking about the locally compact case, then, well, let me see. Sorry, I'm just thinking.
It's supposed to be a single constant
Hmm.
substance, like mu1 cos mu1
Mhm.
is equal to a single constant times mu1 cos
Hmm.
mu1 cos mu.
Yes.
So, well,
Well, okay, this is group one, group two.
you've got two measures on mu1, mu1,
Hmm.
mu1 and mu2.
Yeah.
And then two measures on mu2, mu1 and mu2.
Mm-hmm.
And the question is, you look at mu1 cos mu1 and compare it with mu1 mu2 cos mu2. So mu1 cos mu1 cos mu.
Mm-hmm.
That's one measure. Then the other measures is mu cos
Mu2 cross.
I guess it should be G and H, but the numbers are not, are kind of mixed up. So
Yeah.
it should be G and H.
Okay.
Because, number one,
Oh, just okay. This stays. Okay, I'll call this G. Call this H.
you have two measures on G and H. So
Mm.
the first one is number one,
Mm.
and it's mu1 plus mu. And then the second one is mu2 plus mu2 plus mu2. And so you know that mu1 is a monopole of mu2, and mu1 is a monopole of mu2.
Mm-hmm.
Okay, but how does that translate into the product in the monopole of the product? The two constants.
No, you have a, okay,
The C1 and the C2.
the C multiplied on the
C
U1.
and K.
The C1 for mu have the C1 and the
Wait.
well,
Okay. C times mu1.
But then you want a C mu1
Yeah.
plus a K mu1.
Yeah.
U1.
Yeah.
well, what are the two measures on the product, G class 8? Seems to me the two measures are mu1 plus mu1
Mm-hmm.
and mu2 plus mu2. If you haven't got the two.
Yeah, but mu2 is is a constant of mu1, no? Up to
Well, but before that makes sense, you have to, before that makes sense, you have to follow the new two. Well.
Okay, so
that's
take the
before you put-
constant away in that case.
Before you put in the constant.
Is-
So the two measures are you one, the first measure number one, measure number one is mu1 plus mu1. Measure number two is mu2 plus mu2. And the individual measures, mu1 and mu2 are one of the smaller than the other.
Yeah.
Same for the mu1 and mu2, one is the more than the other.
Yeah.
Well, I'd just like to know how that, I'd like to hear you calculate, speaking of calculation. How does that translate into, the product measure, the first product measure being a multiple of the second product measure?
Well, if mu1, okay, if this is true for our first group, and I should probably put.
I think it's the computation for no sentence later because we're out of time. Okay, George. Good more. Break, and I need more speakers.
As I said, anything involves a computation, so there should be at least one computation. Almost said once that every paper should include at least one proof.
Well, it's a way out because
Every lecture, might be lecture. This is an election. Okay, yeah.
But we're out of time.
Well, we haven't started. So.
No, we've been half an hour doing it. It's half an hour.
Okay, but what I'd like to, you have the answer, because why, one of those measures is a single constant times the other is the other.
Well, yes, I can see why.
Sorry,
I can see why.
I can't hear you.
Yes, I can see why.
Then what's the cost?
Well, CK.
Okay, good. Okay. Oh, but as I said, I like to see it calculated. You were holding back, for something because you said it was calculated.
Well, okay. I will type that up all in my notes and I will send it out to you.